Hi everybody, and welcome to this video on energy changes in chemical processes. Before you start this video, you should get a copy of these fill-in-the-blank notes. They are on Moodle or they are at the side of the classroom. So let's talk about the changes of energy that happen in chemical reactions. So all physical and chemical changes in matter involve changes in energy. Energy is absorbed to break chemical bonds. That means it's taken from the surroundings. And energy is released when new bonds are created because now those molecules are in a more stable configuration, or ions. Energy is transferred between chemical reactions and the surroundings. So if you have a reaction happening in an open system, meaning there's no lid, both matter and energy can be exchanged. Actually, the matter should really be coming out the top of that Erlenmeyer flask. But both matter and energy can be exchanged with the surroundings. However, if you have a closed system, like a flask with a stopper in it, this is my stopper. This is a closed system. Now only energy can be exchanged with the surroundings. Matter is trapped in this closed system. Okay, the law of conservation of energy states that the total energy of the universe, for us the universe is the system and the surroundings together. So the law of conservation of energy states that the total energy of the universe, the system and surroundings, is constant. Okay, so we can't just get energy out of nowhere, and we can't take energy away from something. It has to be transferred between the system and surroundings, and the total amount of energy you have stays the same. Energy is needed for everyday processes. The activation energy of a reaction is the minimum amount of energy needed for a reaction to happen. This is because reactants must collide with enough energy to break bonds for a chemical reaction to occur. Oops, did you catch my typo? So there is a certain amount of energy that the reactants need to have so that those particles will bump into each other with enough energy to break bonds. So if you have some kind of molecule, we'll call that big circle molecule, small circle molecule, they absorb energy from the surroundings. So energy is being absorbed, and that breaks these bonds. Okay, so now you have big and small, and with this energy, these particles are going to bump into each other, and they are going to form new molecules of one big circle, one little circle, and they're also going to, because they're now in a stable configuration, they're going to release energy. Okay, and this energy that is stored in chemical bonds is chemical potential energy. So physical or chemical changes can either be classified as exothermic or endothermic. And to decide which one is happening, we need to compare the energy of the products and the reactants. So let's have a look at some characteristics of exothermic and endothermic reactions. So in an endothermic reaction, the reactants have less energy than the products. And energy is absorbed by the system from the surroundings. So energy comes, this is one where there's more energy in the surroundings and it's going to transfer into your reaction. There is a net gain of energy from the surroundings. So what this means is that it feels cold. So as the energy is being taken away from the surroundings and being absorbed by the reaction, the surroundings are going to start to feel cold. You're losing that kinetic thermal energy as it is being used to break chemical bonds. In an exothermic reaction, the reactants have more energy than the products. So energy is, this one should say released. Energy is released by the system to the surroundings. So there is a net loss of energy to the surroundings, and this makes the surroundings feel hot. Okay, actually, this is an important distinction. So this means that the surroundings feel cold and the surroundings feel hot in endo and exothermic reactions. Okay. So let's look at one way you can show the energy of reactions, and that is in an energy level diagram. So in these diagrams, the energy of the products is this line here. It's red on my copy. And this is the energy of the products. So what you can see happening is that the energy of the, that should say reactants. Did you catch it? Okay, so the energy of the reactants, here there's a little bump. This is the activation energy. So this is the energy required to start that reaction. So you have the energy stored in the chemical bonds of your reactants. It takes some energy to break those bonds and have your molecules or your ions collide with each other. And then energy is, in this case, released to the surroundings. So here we have a transfer of energy. So the reactants have more energy than the products. So this is going to be an exothermic reaction. So the energy in the chemical bonds of the products is lower than the energy in the chemical bonds of the reactants. Okay, what about this one down here? So here's the energy of your reactants. They need a certain amount of energy, activation energy, in order to break the chemical bonds apart and create those collisions. And then here are the products. So you can see overall energy has been absorbed. You only had this much energy to start. You had this much energy to finish. So that had to come from somewhere. So this amount of energy here, this was absorbed from the surroundings. And this up here, this amount of energy here, this was released to the surroundings. So this is an endothermic reaction. Another way that energy is talked about is in terms of bond making and bond breaking. So the energy that is used to get the reactants to this high point where they are going to be colliding, this is energy that is released from bond breaking and then, absorbed by bond breaking. And then this energy here is released from bond making. So reactants, this is where you're breaking bonds. Products is where you're making new bonds. Okay, so an energy level diagram of an exothermic reaction looks like this. Endothermic looks like this. I find it easiest just to think about comparing my reactants and products and realizing that in an exothermic, the reactants have more energy, and in an endothermic, the products have more energy. Okay, but you can also graph the temperature of the surroundings. So if you have a reaction happening in, say, an aqueous solution in a flask, meaning it's in water in a flask, if you put a thermometer into that water, you would be measuring the temperature of the surroundings. You're not actually getting that thermometer all the way down to the level of bonds breaking and bonds making. You are actually just measuring this difference. You're measuring if energy is released to the surroundings, meaning released as heat, or absorbed from the surroundings, so it's losing heat. So here we have, this is the time of the reaction. Over time, in this first graph, the temperature is increasing. So the surroundings are getting more energy. So this is what an exothermic reaction looks like. Because over time, you are getting more energy, right? This energy is being released from the reaction and is making your surroundings warmer. On the other hand, down here, over time, our temperature is decreasing, and that's because the heat that was in the solution, so in my example, in the water, is being absorbed in order to activate this reaction and create those bonds in the products. So here, this is an endothermic reaction, and the difference is that in these graphs, you are measuring the temperature of the surroundings, and in these energy level diagrams, you're measuring energy of the reactants and products, so the energy at the molecular level, okay? The energy stored in bonds or released by bonds. Okay, I hope that's clear. If you have any questions, you can ask me on our team or ask me in class. Have a good day.